networks can have multiple outputs, right? Like predicting the probabilities for 10 different classes of images. How do you track change when you have multiple outputs and multiple inputs?
For that, you need to generalize the gradient. And that generalization is the Jacobian matrix.
The Jacobian.
It's just a way to organize all the possible cross-influences. If you have, say, m different output functions, and each one depends on n different input variables, the Jacobian matrix captures all of it.
So in the source example, we have two output functions, f and g, and two inputs, x and y. So the Jacobian J should be a 2 by 2 matrix.
That's right. And the structure is just, you stack the gradients.
Exactly.
The first row of the Jacobian is the gradient vector for the first output function, f. The second row is the gradient vector for the second output function, g.
So for our example, row 1 would be the gradient of f, 10yx 5x squared, and row 2 is the gradient of g, 5 8y to the 7th.
And that single 2 by 2 matrix now holds everything. It tells you the rate of change of every single output with respect to every single input. More generally, if you have an output vector y that's a function mapping n-dimensional space to m-dimensional space, the Jacobian is an m by n matrix.
Right, the intuition here feels important. The m rows are the m different outputs that can change, and the n columns are the n different inputs that are causing the change. It's really just an organizational tool. It's for efficiency.
It's pure efficiency. Instead of calculating m different gradients one by one, you calculate them all at once and store them in this one object. And this matrix is exactly what we're going to plug into the vector chain rule.
Here's where it gets really interesting.